Hello, this is another Ansys Fluent tutorial which is provided by Ansys itself. This is a tutorial of multiphase flow, a mixture of water and air, and in this tutorial we are going to compare the result of mixture model with the Eulerian model. So if you look at the problem description here, we have a T-junction, we have a geometry of a T shape, which the flow is entering from the bottom. We have the velocity inlet at the bottom with the water at the speed or the velocity of 1.53 meter per second, and air at the same velocity with the volume fraction of 0.02 and the bubble diameter of 1 millimeter. So air is basically is assumed to be bubbly inside the water with the bubble diameter of 1 millimeter. And then you have a junction here, which either the flow can go to the right or to the top, and the type of the outlet boundary conditions you have is flow rate weighting, and the flow rate weighting is actually outflow with the flow rate weighting of 38% to the right and 62% at the top. So I'll go to Ansys Fluent, or I can start with from the beginning, from the scratch, from Ansys Workbench, and I just drag and drop a Fluent case here. I double click on the setup, and this is a 2D problem, and I make sure to have this double precision on, and I press OK. So the geometry and the mesh is already created. What I need to do is just to import them to my Ansys Fluent from my from the place that I have saved the mesh. So you go to import and you read the mesh from where you have your case stored. So this is going to be here. It's called tree mesh. Very simple mesh, actually with no inflation layer to the walls. And if you look at for example the outlet and the inlet, so if you just look at the velocity inlet, so you see that the velocity inlet together with outflow 5 is actually the top, and outflow 3 is the one to the right. So if I display everything again and I go to general, this is a steady state case, and the type of solver is pressure based. The gravity is on, the magnitude of gravity is minus 9.8 in the y direction. The material that we have, as we said, it's water and air, so the air is already created. I'll just need to go to Fluent database and look for the water liquid, and you just copy it, and I close. The models, the multiphase model, we start with the mixture, the simplest multiphase flow model available in Ansys Fluent. The slip velocity is on, and I'll put the implicit body force to on as well. The number of Eulerian phases are 2. It's water and air. So I press OK. And then the viscous, I'll just go for K epsilon model with the standard wall function, but I may probably want to use realizable, because realizable is more accurate when you have flow with bending and things that may happen in the bendings here, for example in this specific geometry. So I'll change it from standard to realizable. And then regarding the phases, I'll go to list show all in the phases. The primary phase in this simulation is of course water, because it's basically dominated by water. I may want to change the name to water as well, so I press OK. And the secondary phase is actually air, with the phase material of air. This is not a solid particle, so the granular options are not applicable in this simulation. So I'll just make them off. And as I said, the air bubble diameter is like 1 meter. So this is 0.001, and I press OK. I'll close this now. And if you go to the phase interactions, what you have here is several type of phase interactions in this specific model, mixture model. So there is one option which is a drag between air and water, the drag between the water and air bubbles. And the type of models we have several options here, but I'll go with the default Schiller-Neumann. You may want to specify the slip velocities and the mass transfer mechanism, which is not available here, or the surface tension. But at this point in this simulation, I'll just have this drag between water and air bubbles. So I'll press OK. Then I'll just jump to the boundary conditions. So if you remember, in the velocity inlet, I'll keep the specification method for turbulence as intensity and viscosity ratio, with 5% turbulence intensity and 10% turbulent viscosity. But if I go to this velocity inlet and I double click on the water, for example, then you have the possibility to specify the velocity magnitude, which, if you remember, was 1.53 for both water and air. This is how the problem is defined. Both velocity and the air bubbles are actually being transported in the inlet with the same velocity. And for the air itself, you need to go to multiphase tab and put the volume fraction to 0.02. This was the volume fraction that was given in the problem description. So I press OK, and then regarding the outflow tree, which was the one to the right, if you remember, I showed in the beginning, the flow rate weighting was 0.38 according to the descriptions and the problem descriptions, and the one for outflow 5, which was the one on the top, was if I'm not wrong, it was 0.62. I can take a look. Yeah, it's 0.32, 62. And then double clicking on water, double clicking on air, and that looks fine. Then what I need to specify is this operating conditions as well. The gravity is already selected, but then I would like to specify the operating density of this problem to 0, and that is because actually when Ansys calculates the pressure, it redefines the fluid pressures by removing the hydrostatic components, and actually based on the average of average density. But here, by setting the operating density to 0, I will force Ansys Fluent to include the hydrostatic pressure explicitly in the final post-processing contour plots. So I'm putting this to 0 because I would like to see the hydrostatic pressure included in my final static pressure contour plots. And then I press OK. Then I'll just go to methods. The pressure velocity coupling, I will use coupled, and then presto for pressure, and I'll go for third order. For the momentum, I'll go with third order MUCCL, and perhaps for volume fraction I'll go with quick, and then third order, and the third order, which are probably the most accurate solution methodology for this specific problem. Then I'll go to control, flow current number I'll put to 40. I'll keep the same as it is, and I just need to initialize the problem, or maybe I need to specify the residual monitors as well, make it a little bit smaller so that it doesn't converge so fast, and I press OK. For this specific problem with the multiphase flow transports, complex a bit, hybrid initialization is the best. I press initialize, and then I'll go to run calculation, and I run it for some 600 iterations, and we'll see how fast it converges. So you see the iterations now, and continuity, velocities, k, epsilon, and volume fractions are actually below 1e minus 4, and it's pretty fine converged right now. So I'll just continue the iterations for some 100 more, and then I'll stop the iterations, and we can take a look at the results together. See that epsilon is quite flat at this point, and after 500 iterations all other residuals are also getting flat. So I think I'm happy with the results now with the convergence, and then I'll go to post-processing. Maybe I would like to take a look at the fluxes now, the mass outflow in the mass flow rate in the outflows, and the velocity inlet. Let's take a look at mixture first. You see that in the outflow 3 and outflow 5, the ratio of 62% to 38% is valid, and the net value is very close to 0, meaning that the mass convergence criteria is set. You can take a look at water and air as well, so it's not that much different. I'll go to contour, and I plot, for example, I can plot the contour plot of a static pressure with the field option on. You can clearly see the hydrostatic pressure build up in this vertical column. As you see, the hydrostatic pressure now is included in the static pressure, and maybe we can take a look at the vector plots, for example. Vector plot of velocity, the phase mixture. Then I just increase the scale a little bit to have a better look. So here you see that the flow has a higher velocity to the top of the arm, and in the beginning of this arm, at the bottom, you have this recirculation area, which is quite obvious and clear in this area. So in this problem there is a recirculation phenomenon involved, and perhaps we can conclude that the mixture, which is the very simple multi-phase flow model, is not that accurate. We can also take a look at some other parameters like the volume fraction of water. We can have this field option on as well. So here is the volume fraction of water. You see that is completely or almost filled with water. But then we can take a look at the volume fraction of air as well, and you see that in the horizontal part, which we call it arm, actually due to the gravity and the buoyancy force, the air bubbles has started to move further to the top, and actually the gas pockets are accumulated on the top further downstream. You see that there are gas pockets accumulated on the top, and it's probably or most probably, or actually it's the buoyancy force that is acting on the less dense face here, and it's forcing it up to the top of the horizontal part. But keep in mind that how big is this gas pocket, because when we come to the Eulerian model, which is more accurate, we want to compare this extent with the Eulerian model as well. So I think we are fine with this mixture model now. We are done, and we can jump to the Eulerian model. So what I need to do is to go to the multiphase model, and then I'll pick Eulerian. I will not touch these Eulerian parameters because these are not valid here. I press OK, and then regarding the viscous model, it's the same k epsilon model realizable with the standard wall function, and I will not change the turbulence multiphase model from mixture to disperse because the dispersion is not that significant in this problem. So I press OK, but then I'll go to phases here, and then I'll go to interactions. So the difference between the Eulerian model and the mixture model that we used before is basically that the Eulerian model is much more accurate, because in the mixture model, the inertia, when the bubble exists, the bubble inertia can be neglected simply. But in the Eulerian model, this bubble inertia are taken into account, and Eulerian model has some other non-drag forces included in the model itself, which does not appear or does not exist in the mixture model. For example, here you can see that beside the drag force that you had in the mixture model, now you have the lift force as well, which talks about the effective it talks about the lift force on the air bubbles. So I have already had the drag part, but when it comes to the lift, I will go for I don't know, for this model, which is Legendre Magnetet. This is probably a French name. I hope I have pronounced it correctly. And then I press OK. Regarding the other parts, I will not touch them again. There is no such mass transfer mechanism. If I want to have it on, there is no much like cavitation or I don't know, mass transfer between the water and phase, so I will not activate this one for now. Of course you can have the surface tension here as well, but I will not touch that one as well, and I will press OK. So the rest is the same, and I will not initialize it because we have already a good solution here from the mixture, so I'll just need to run the calculation from what we had before. I press OK, and I run it for some 600 iterations. So what we would like to see here, what we would like to compare here, is the effect of the lift force and the Eulerian methods that we have implemented in this simulation compared to the mixture model. So I will wait until the solution is converged, and then we go back to the final results and compare. We can compare the static pressure, the velocity, and the volume fraction of water and air. think I'm fine with the converge solution. Then I'll go to contour plots of, for example, volume fraction of air, and I press on the field. Alright, I have extracted the volume fraction of air for these two models that we used. The one on the top is from the Eulerian and the one on the bottom is from the mixture. So if you compare the volume the volume fraction of air for the mixture model, so you see that this this air pocket on the top is much bigger and it's much more elongated, but the one for the Eulerian, actually the air is much more transported with the water before it accumulates on the top. And the reason is basically, if you look at the if I take a look at the pressure or the velocity or the pressure contour plots in the Eulerian, let me explain on the contour plots of, let's say, velocity. So here you see that this is the one with the Eulerian. So basically what happens is that the buoyancy force is working in the positive y direction, and it's forcing the airs that are coming from the vertical pipe into the horizontal pipe to accumulate on the top. But on the other side, the lower pressure, the higher pressure on the top of the pipe is acting downward. So the inertia is actually working in opposite direction of the gravity, and that is the lift force that we have included in this Eulerian model, and which was not available in the mixture model. So you see here that the lift here is working against the gravity, so it postpones or it delays the accumulation of the air gas pockets on the top of this region. So that was basically this tutorial, the difference between the Eulerian and the mixture, and showing how more accurate is the Eulerian model, and basically how to set up a multi-phase flow model using Eulerian and mixture models. I hope you have enjoyed it. I'll come back with more tutorials later. Thank you.